So in today's lecture, we will see the differences between the scanning electron microscopy and transmission electron microscopy. Okay. So in today's lecture, we'll see what are the differences between the scanning electron microscopy and transmission electron microscopy. SEM represents scanning electron microscopy. Okay, whereas TEM represents SEM represents scanning electron microscopy, and TEM represents transmission electron microscopy. Transmission electron microscopy. Okay. So of course, both this transmission electron microscopy and scanning electron microscopy, both are used for the characterization of the nanomaterials. Both are used for the characterization of nanomaterials. Okay. So the nanomaterials have been fabricated, as we have seen in our previous lecture, that they are fabricated by using different process techniques like physical vapor deposition, chemical vapor depositions, and in physical vapor deposition we have seen what is DC magnetron sputtering and what is RF sputtering, what is sputtering technique, what is E-beam evaporation, what is thermal evaporation. Whereas in CVD also we have seen certain methods like soul gel methods and all. Okay. So after that we have seen certain characterization tools. So in that characterization tools we have seen what is an X-ray diffraction technique, and what is scanning electron microscopy, and we have seen certain another characterization technique like transmission electron microscopy. We have seen what is neutron diffraction, what is STM, what is SPM scanning probe microscopy, what is scanning tunneling microscopy, what is scanning capacitor microscopy, SCM. Like that, we have seen different mechanisms and different tools for characterization of these two techniques. So in today's lecture, we will see what are the differences between this scanning electron microscopy and transmission electron microscopy. So scanning electron microscopy and transmission electron microscopy, as we told, that both are used to characterize the given nanomaterials. So in first case, the scanning electron microscopy is used to study the surface morphology of the films or the surface morphology of the sample, whereas in transmission electron microscopy is used to study the total structure of the structure of the material. Whereas in SEM we need certain large material. We need the sample in a large quantity, whereas in TEM we require a small quantity. So that is FESEM we have, and high resolution HR-TEM also we have, high resolution transmission electron microscopy, and we have scanning electron microscopy, field effect scanning electron microscopy. Okay, so we'll see. So if you come to the history of these two particular techniques, so Zurowski in 1942, the first SEM for bulk samples was introduced, whereas in case of TEM, 1931 itself. So before the discovery of SEM, TEM was introduced, right? So 1931, Max Knoll and Ernest Ruska developed the first TEM microscopy, and Zurowski et al. 1942, first SEM for bulk samples. Okay, so 1965, first commercial SEM scanning electron microscopy was introduced by Cambridge Scientific Instruments, right? First commercial scanning electron microscopy. So here, TEM is constructed in 1931, as we told. Von Andron first STEM in 1938 by rastering the electron beam in a transition electron microscopy, where the resolution at that time is approximately 50 nanometer. Today it is very much less than 1 nanometer. So morphology only at that time. So total today analytical instrument is used. So this is what regarding this. Whereas in TEM, this group first interested in further developing the resolution of cathode ray oscilloscope. So oscilloscope, this group in the sense which was introduced in the year 1931 by Max Knoll and Ernest Ruska, developed the first TEM microscopy. Considered the first electron microscopy, the group was first introduced in further developing the resolution of cathode ray oscilloscope. After World War II, Ruska was finally able to produce the first transmission electroscopy with 10,000 resolution power. So basically, we see what is a scanning electron microscopy. It is a microscope that produces an image. It is a microscope that produces an image by using electron beam that scans the surface of a specimen inside a vacuum chamber. right? The SEM is a microscope that uses electrons instead of light to form an image. Since their development in the early 1950s, scanning electron microscopes have developed new areas of study in the medical and physical science communities, right? So what we can study from this scanning electron microscopy in the sense, so the parameters that we can study from scanning electron microscopy is the first we can see the geometry, that is the topography and morphology of the films, and we can see the chemistry of the films, and we can also understand what is the crystallography, the crystallography that is introduced, right? So what is the type of crystal, and what is the orientation of grains, how the grains are oriented in different directions. In situ experiments, reactions with atmosphere and effects of temperature. So these are the certain parameters what we can study in SEM. SEM, we know that SEMs use an electron beam to image samples with a resolution down to the nanometer scale. So the electrons are emitted from a filament and collimated into a beam in the electron course. The beam is then focused on the sample surface by a set of lenses in the electron column. So scanning electron microscopy produces detailed magnified images of an object by scanning its surface to create a high resolution image. So SEM does this using a focused beam of electrons. So the advantages of SEM are SEM scanning electron microscopy has a broad range of research and practical applications. It provides detailed topographical images, providing versatile data. Given proper training, SEM equipment is straightforward to operate and specialist but user-friendly software supports it. So modern scanning electron microscopy data comes in digital form. It's a rapid process and instruments can complete analysis in under 5 minutes. There is a degree of sample preparation necessary, but usually this is the very this is usually minimal case, right? So what is a transmission electron microscopy? Transmission electron scanning electron microscopy, the resolution of the image is limited only up to 10 to the power 10 to 20 nanometers, right? So this will not be useful to view the internal features of an atom or the morphology of a sample of size say 0.2 nanometers. So to view that, to see that particular internal morphology of this film of low thickness around zero point 0.2 nanometer, people will start studying the transmission electron microscopy. That is what TEM. So thus, to example, the size of up to 0.2 nanometer, the transmission electron microscopy can be used. In this microscope, the image is obtained by transmitting electrons through the specimen. That means electrons. It means the electron beam will transmit into the sample, right? The electron beam rays transmit into the sample, and we can study the whole structure of the film. Whole structure of the film can be studied using this particular transmission microscopy, right? So in this microscope, the image obtained is by transmitting electrons through the specimen. So this is what we can see the differences between the scanning electron microscopy and the transmission electron microscopy. Here, if you see, in case of scanning electron microscopy, we have the electron source, we have the anode. This is a lens, right? And that is a BSC detector. That means backscattered electron detector, and secondary electron detectors. That means if we place a sample here, and if we try to beam the X-ray, if we try to beam the rays, right, from the source, then this particular sample will take that rays, and we can study the surface thickness, surface morphology of the sample, and that morphology can be detected using the BSC detector. BSC detector in the sense secondary emission detector. So, right. So that means only on the surface of the film only we can study the particular morphology. Whereas in case of transmission electron microscope, we have the same. We have the electron source, we have the anode, of course, we have the samples. But in case of scanning electron microscopy, we have placed a sample at the bottom of the bottom bottom of that particular instrument, right? Bottom of that particular sample holder, right? Whereas in case of SEM, the sample is placed in the middle. Middle is placed. That means the total rays will transmit. The total rays will transmit into the specimen, and we can study the whole morphology, whole structure, whole internal structure of that particular film. So SEM is used only to study the surface analogy, and whereas STEM is used to study the internal morphology, internally how the atoms, what is the dimension of that particular sample, what is the dimension, what is the dimension of that particular sample. At the same time, the dimension of the sample at very low resolution, So that's what when we need to use a sample around 0.2 nanometer, when we use the sample of thickness of 0.2 nanometers, So it is very difficult to study the surface of the film. So that's why people go for high resolution. In that high resolution, people will go for transmission electron microscopy. So this is what the differences between the SEM and transmission electron microscopy, right? So what does it look? What does it look like? So here we have the AFM cantilever tip, and we can study the surface of the ant head. So if you put an ant, right, we can see the ant head like this. So we can see the blood cells. Okay, we can see the calcium phosphate crystal here, and microstructure of plain carbon steel that contains 0.44% weight of carbon, and diamond thin films, that means numerous multifaceted microcrystals can be studied by using this particular analysis techniques, that is called SEM and TEM. So this is what we can study, the surface analogy, that surface of the ant head only we can see the surface of that particular ant, right? We can see the surface, but we cannot study the internal structure of that particular ant, right? So to study that internal structure, we need to go for some biological methods, but whereas to study the physical interpretation of the internal structure, then people will go for transmission electron microscopies. So this is what the instrument in brief that we have. So electron gun, we have gun alignment controls and pneumatic airlock valves and condenser lenses, and objective aperture, we have scanning coils, objective lens, and we have motorized stages and simple and sample chamber, so which is placed at the total bottom of that particular instrument, at the lowest stage, right? So the components of the instrument, we have electron gun, that is what we are telling, the filament. We have some electromagnetic optics, scan coils, sample stage detectors, vacuum system, computer hardware and software, right? Computer hardware and software, which is not trivial. So these are the electron guns. We want many electrons per unit area, there is high current density, and as small electron spot as possible. Traditional guns, thermionic electron gun, electrons are emitted when a solid is heated, right? So lithium, barium crystal, that is a modern field emission guns, that is what we call as FEG. So there we use cold guns. A strong electric field is used to extract electron. Single crystal of we etch it to a thin tip. Our traditional detectors, these are the BSc in the sense backscattered electrons detector. So in case of backscattered electron detectors, we go for solid state detectors. These all we study in case of scanning electron microscopy, right? So secondary electron detector we have, and we have the secondary electrons, we have Everett Thornton detectors, backscattered electrons, solid state detectors, X-rays, EDAX, that is what we energy dispersive spectrometers, right? So how the SEM works? The SEM uses electrons instead of light to form an image. So a beam of electrons is produced at the top of the microscope by heating of a metallic filament. The electron beam follows a vertical path through the column of the microscope. It makes its way through electromagnetic lenses, which focuses and direct the beam down towards the sample. Once it hits the sample, the electrons, or the backscattered electrons, are ejected from the surface of the sample. Detectors collect the secondary or backscattered electrons and convert them to a signal that is sent in viewing a screen similar to that one in ordinary television that we have seen, that we will see producing an image. So how do we get an image? This is what the mechanism where we get the image, right? So electron beam sample interaction. The incident electron beam is scattered in sample both elastically and inelastically. This gives rise to various signals that we can detect. More on that on next slide. More that we can detect. Okay, more we can see in the next slide. The interaction volume increases with increasing accelerating voltage and decreases with increasing atomic number. So this is what we can see, the electron beam. So low accelerating voltage, medium accelerating voltage, and we can see the high accelerating voltage. So see the sample variation, right? See the high accelerating voltage, whereas here we have high atomic number, medium atomic number, and low atomic number. So signals from the sample are scattered in different directions. That is what we can see, the scattered electrons, backscattered electrons, incoming electrons, Eiger electrons, X-rays of course, and we see some cathode luminescence lights. So where does the signals come from? So signals come from diameter of interaction. Volume is larger than the electron spot, resolution is poorer than the size of the electron spot. So this is one of the dimension where we can see. We have the incident electron beam, we have the scattered electron beam, scattered electron conduction, backscattered electrons. So primary X-ray. So we can see here, this is a primary X-ray excitation. This is the incident electron beam, scattered electron beam, Bremsstrahlung continuity equation, cathode ray luminescence excitations. So this is what the secondary electrons is generated from the collision between the incoming electrons and the loosely bounded outer electrons. And the low energy electrons, approximately 10 to 50 electron volt, only scattered electrons generated close to surface secondary and is obtained. Number of scattered electrons greater than number of incoming electrons. So we can differentiate between two stages, that is scattered electron 1 and scattered electron 2. So this is what we can see in case of scattered electron 1 and scattered electron 2. So this is what the backscattered electron, a fraction of the incident electrons is retarded by the electromagnetic fields of the nucleus, and if the scattering angle is greater than 180 degrees, the electron can escape from the surface. So there is a elastic scattering where higher energy electrons are used. So there are very favor backscattered electrons and secondary electrons. So we can differentiate between BSE1 and BSE2, right? So BSE versus scanning secondary electrons. SE produces high resolution image than BSE. By placing the secondary electron detector inside the lens, mainly SE1 are detected resolution of 1 to 2 nanometer is possible. So these are the X-rays, photons are not X-rays, photons not electrons. Each element has a fingerprint X-ray signal, poorer spatial resolution than backscattered electron and scattered electron. Relatively, few X-ray signals are emitted and the detector is inefficient. Relatively, long signal collecting times are needed. So these are some of the comments that are generally raised during the resolution, right? So this is what regarding the scanning electron microscopy. And whereas in history of TEM, so if you see the history of TEM, you have seen so that we can go for the TEM when the thickness varies up to 0.2 nanometers, right? So how the principle of working of TEM takes place. Electron possesses wave-like character, right? Electrons emitted into the vacuum from a heated filament with the increased accelerating potential will have small wavelengths. Such higher energy electrons can penetrate distance of several electrons into a solid. If these transmitted electrons could be focused image, then which much better resolution. Focusing relies on the fact that electrons behave as negatively charged particles and are therefore deflected by electric or magnetic fields. So these are the different parts of TEM. So we have the electron cannon. So we have electron cannon, and we have that vacuum pump systems and water supply to cool the instrument, vacuum chamber for observation, screen for menu, and image display and operation panels, right? So we have the electron source. The electron source consists of cathode and anode. Cathode is generally the cathode, the tungsten film which emits electrons, which when being heated, a negative cap confines the electrons into a loosely focused beam. The beam is then accelerated towards the specimen by the positive anode. Electron beam is tightly focused using the electromagnetic lens and metal apertures. A platform equipped with a mechanical arm for holding the specimen and controlling its position. And we have the electromagnetic lens system, then objective lens, projector lens, and we have phosphorescence screen also. So in case of transmission electron microscopy is an instrumental technique that is used to tiny focused beam of electrons. These electrons interact with a very thin and tiny sample, usually only a couple atoms thick. After passing through the sample, the electrons have changed course slightly and are detected by a photographic film or CCD camera. So TEM theory, if we go for the theory, we have the de Broglie wavelength of electrons, where we have the matter of symmetry concept, and sometimes behaves as a particle, sometimes behaves as a wave. And if we see that particular theory, de Broglie's hypothesis, and when confined to wavelength, then we have the lambda equals to h by under root of 2m e naught. 2m naught rest mass, E is the energy, and m naught c square is the velocity of light, where h is a Planck's constant, and E is the energy of the accelerated electron, and c is the speed of light. So because electrons have wave particle duality properties, they can be produced at specific energy and wavelength and then analyzed after being affected by the sample. So the maximum resolution that can be obtained is given by d equals to lambda by 2n sin alpha, where lambda is a wavelength and the numerical aperture is what the parameter that can be affected by using this particular sample, by using the TEM, right? So that generally the TEM consists of electron gun made from a tungsten filament or lanthanum hexaboride crystal. The E gun is charged about with 100 to 300 kilovolts before an electron's of principal energy will be released from the source. Then a series of electromagnetic and electrostatic lenses are direct the electrons into a beam. So there are three set of lenses of a typical TEM. So one is the condenser lens, objective lens, and projector lens, right? So projector lens expands electron beam into electrical form onto analysis screen or CCD. Magnification adjustments are made by varying the current through the quadrupole or hexapole lenses. So what are the components that are generally used? The components that are generally used are vacuum components. The vacuum system is around 10 to 4 to 10 to 9 pascals, very important to prevent arc between cathode and ground. Main free path of electrons, better beam focusing, less interaction with gas molecules. Sample components are sample grids, usually 3 mm diameter mesh string with 1 to 100 micrometer size pairs made of copper, molybdenum, oil, or platinum. Samples inserted into section with air locks to prevent large decrease in vacuum pressure. Stages are designed to adjust the sample orientation when inside the TEM or more accurate readings. Components. So we have electron lens components. Electron lens focus parallel rays at a constant length, and transmission electron microscope lens are usually electromagnetic, made of iron cobalt, or nickel cobalt because of their magnetic properties like magnetic saturation, hysteresis, and permeability. Aperture components filter electrons that can stray from beam path and affect image quality, and decrease beam intensity helpful with beam sensitive samples can be fixed or movable depending on the quality of the instrument or manufacture. Made of metallic substances thick enough to stop stray electrons but allow axial electron through. So electron gun is a high energy electron beam is produced by thermionic emission from directly heated tungsten filament. This electron beam is accelerated by the anode towards the specimen, and we have magnetic condensing lenses. The electron beam can be converged or diverged by these lenses. These lenses are usually of magnetic type, that is current carrying coils, right? So the focal length can be adjusted by the current through the coil in the magnetic lens. So if you see the construction, magnetic condensing lens is used to condense the electron and is also used to adjust the size of the electron that falls onto the specimen. The specimen is placed in between the condensing lens and objective lens. The magnet objective lens is used to block the high angle diffracted beams. The aperture is used to eliminate the diffracted beam, and in turn it increases the contrast of the image. The magnetic projector lens is placed above the fluorescent screen in order to achieve higher magnification. An image can be used by using closed circuit diameter camera. So this is what the internal structure of the transmission electron microscope. We have the electron gun, where we have the magnetic condensing lens. So they are collimated by that and they are allowed to fall on the specimen. After studying the internal part, they are again sent through the structure by using magnetic objective lens, and to get the fine beam, apertures are placed, and these apertures are further projected on the projector lens, the magnetic projector lens, where we can obtain the image and the fluorescent screen. So this is how the bright field and dark field images takes place, right? So working stream of electrons are produced by the electron gun and is made to fall over the specimen using the magnetic condensing lens. Based on the angle of incidence, the beam is partly transmitted and partly diffracted. Both the transmitted beam and the diffracted beam are recombined at the evolved sphere. So sphere of reflection, which encloses all possible reflections from the crystal satisfying Bragg's law to form an image. The combined image is called the phase contrast image. So in order to increase the intensity and the contrast of the image, an amplitude contrast image has to be obtained. This can be achieved only by using the transmitting beam, and thus the diffracted beam has to be eliminated. Now, in order to eliminate the diffracted beam, the resultant beam is passed to the magnetic objective lens and aperture. The aperture is adjusted in such a way that the diffracted beam is eliminated. Thus, the final image obtained due to the transmitted beam alone is passed to the projector lens for further magnification. The bright field image direct obtained is purely due to the transmitted beam rule alone. The dark field image obtained due to the diffracted image. So why we need to use the TEM? So a TEM is able to form an images of samples and atoms of tens of thousand atoms, smaller than of any visible light microscope. Usually, the stage tuning, a tilt series can be developed to solve 3D images of the sample, and scanning types uses the bright field, diffraction contrast, dark field image, crystallographic, that is what you can say the lattice defects and voids, and biological specimen, meaning and subatomic ratios. So what are the advantages and the disadvantages of using the transmission electron microscopy? The advantages are very high resolution, requires very simple little sample for testing of that particular image, and it is used for quantitative and qualitative, and it can be modified in many ways to account for different substances and requirements. So cons, the disadvantages are pros, and the advantages cons. We need a tough sample preparation. Hours that particular image to find the image, we need to lot of time is required to run few images, right? Small field of view may take several runs to find what is being studied, and there is a chance of sample destruction also, especially the biological samples, right? So what are the advantages? It can be used to it can be used to study the specimen of size up to zero point 0.2 nanometers, right? The magnification is 1 lakh times greater than the size of the object. The high resolution, the resolution power is 1 to 2. The disadvantages are the specimen should be very thin. It should not be. It is not suitable for thick samples. 3D image cannot be obtained. There are chances for the structural change during the sample preparation. In case of biological samples, the electrons may interact with the samples, which may even damage the sample. These are applications. The main application of TEM in nanoscience is used to find the internal structure of nanomaterials. It is used to find a 2D image of very small biological cells, viruses, and bacteria. After all, in the summary, we can see that TEM is useful for small nanoscale analytes. TEM can create 3D images of the sample. TEM can be modified different types of molecules in atom. TEM is not cheap. It is, of course, it is very costly item, and TEM is good, and that's the way the cookie crumbles. So these are the references what we have seen by having certain books called Fundamentals of Material Science and Engineering by William D. Callister, and we have the Physical Metallurgy, Robert Waldkamp, Physical Metallurgy and Advanced Materials, R.E. Smallman, Physical Metallurgy Samples, Robert E. Harrell, and this one is the Encyclopedia of Scanning Electron Microscope. So overall, if you see the differences between the SEM and TEM, so this is what the instrument difference we can find. This is what the instrument difference we can find between the scanning electron microscopy and the transmission electron microscopy. This is what the sample is placed at the middle, whereas and SEM is sample is placed at the bottom. An electron beam is directly projected on the surface of the sample. Here, in case of TEM, the electron beam is directly penetrates into the sample, and we can see the penetration depth also. That means we can see the chemical structure of that particular sample. So these are what the differences we can see between the transmission electron microscopy and the scatter. We can see the differences between transmission electron microscopy and scanning electron microscopy. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.